Greetings everybody. Our paper is the CFD validation and economical optimization of heat transfer enhancement utilizing carbon oxide nanoparticles in double pipe heat exchanger with various economic conditions before, during and after COVID-19 pandemic. The heat exchangers is widely used for various industries for cooling and heating purposes. The heat transfer enhancements in heat exchangers prevails high quality and cost-effective design and operation conditions. For example, in this reactor, we need the two heat exchangers to control the temperature and to have the best conservation of energy and products. To enhance the heat transfer in heat exchangers, we need to modify the surface area or to modify the overall heat transfer coefficient. The addition of nanofluid or nanofluid additives or nanoparticles additives is used to enhance the thermal conductivity and interfacial area of base fluid. How does non-fluid affect on heat transfer? Nanoparticles concentration, nanoparticles size and flow pattern, bulk fluids rates, flow rate, surface characterizations or the surface characteristics of nanoparticles, nanoparticles bulk fluid interaction, nanoparticles tube wall collision, nanoparticles collision and electrical charges of nanoparticles. The aim of research to investigate the effect of dispersion of carbon oxide nanoparticles on heat exchanger performance under turbulent flow conditions. It is also aimed to simulate the heat exchanger process using CFD package COMSO multiphysics to predict the heat transfer coefficient and temperature profile in axial and radial directions. To find the cost-effective operation by nanofluid additives for various economical conditions through COVID-19. This is the experimental configuration or rig configurations. The double pipe heat exchangers are connected by the cold in the shell and the hot stream in the tube. The cold stream is connected by cooling tower. The cold water will pumped into the shell, and the hot water is mixed by agitation or agitator with the nanoparticles additives and heated, then pumped into the tube in countercurrent configuration pattern. The operation conditions of inlet hot temperature of 43 degrees centigrade, the inlet cold temperature of 15 degrees centigrade, the range of Reynolds number of hot side of 19,000 and 64,000. Then the cold number about 9,000. The agitation speed of 400 rotation per minute. The nanoparticles concentration range of half to 3 gram per liter. Nanoparticles average size of 40 nanometer carbon oxide. The standard deviation of margin of error for no nanoparticles or without nanoparticles about 551, the standard deviation, and the margin of error minus plus 18.8 watt per square meter and dot degree centigrade is about 2% or less, and the 4 nanoparticles case the same or close to single phase. The degree of confidence level about 90%. This is the picture of used particles of powdered copper oxide. Our results revealed that the friction factor and various nanoparticles concentrations from the single phase without nanoparticles and the various nanoparticles concentrations. The less nanoparticles concentration gives the results close to single phase, and we found that the reduction on friction factor for the less hot Reynolds number. For higher Reynolds number, we found that no effect of nanoparticles concentration on the friction factor. For overall heat transfer coefficient in single phase or without nanoparticles, the rising of hot Reynolds number and cold Reynolds number give us the high range of overall heat transfer coefficients. And as we see, the range of Reynolds number in 1000 approach 1000 of value, and as we see in the standard deviation, the about 94 or and the margin of error of 551, and the margin of error is 18.8, and this is too small value as comparing with the results. The CFD analysis or validation analysis, we found that the present work is close to CFD model, and we have good agreements. For nanofluids, the rising of nanofluid concentration will give us a good enhancement in overall transfer coefficients. We found that about 100% enhancement at higher concentrations of nanoparticles, and for further high concentrations, the heat transfer enhancement will be reduced clearly. As shown in this figure, we found the reduction of heat transfer enhancement for further high concentrations nanoparticles by the effect of the nanoparticles falling inside the tube of heat exchanger or heat exchanger tube, because the high concentration of nanoparticles will give us the thickness or nano thickness inside the tube. The thickness will be deposits inside the tube, give us additional heat transfer resistance, so the heat transfer enhancement will be limited in further concentrations. And as we see in the single phase nanoparticles case, we will have a good agreement and close results between the CFD and present work. In this table, we found the enhancement percent for various concentrations and the Reynolds number. We found the optimum conditions is in 2 gram per liter in 64,000 hot Reynolds number, about 114.2%, and in further concentration will be reduced to 94.09%. as we see in by fouling effects. This is the profiles for mixer to see the distribution of nanoparticles inside the vegetation to have an indication of effect mixing between the nanoparticles and the fluid. This is the radial axial velocity and pressure distribution. This is radial velocity and pressure distribution of heat exchanger, and for temperature. The cost, rough cost estimations for three conditions: before, during, and after pandemic. Before pandemic, the oil price was $40 per barrel. The annual cost estimation we found in 2 gram per liter nanoparticles and higher Reynolds number. The minus cost is presented. Without the nanoparticles, the higher costs are presented, and so on. For during the COVID-19, the $30 per barrel oil prices, the little small cost effective operation is observed, and higher and less cost, and so on, for less cost estimations and less cost is observed in minus or in positive actions. For rising the cost of oil prices after the COVID, the much minus values is appears for 2 gram per liter as annual costs, and much cost in positive are appeared. The results showed that the heat transfer enhancement by using non-fluid of concentration range of nanoparticles from 0.5% results in heat transfer enhancement for 40 to 114% for various Reynolds number. Comparison between the CFD and present work for either be a nanofluid and without nanofluid, we have good agreements. We found 2 gram per liter have cost-effective operation conditions for various economic conditions. Thanks for listening.